Is GraphRAG the next evolution in RAG? Will it solve the current problems and challenges in RAG? Couple of months back, Microsoft came with GraphRAG and they claim that there are substantial improvements, especially for queries which require understanding of different sections of text. So watch till the end of the video as we go through information in a text file, index it using GraphRAG, ollama and llama3.1 without using OpenAI APIs. This part is super important and you'll soon know why. And we'll see how to answer various queries. Hi, my name is Joydeep. I have 13 years of experience and have created hundreds of projects in AI. And in this channel, I talk about GenAI, career, and the industry. Please like this video and subscribe to the channel, and as this will motivate me to continue working towards bringing you the latest trends and knowledge from the world of GenAI, and you can build awesome projects in GenAI and bring massive success to your career. Welcome to my channel. Okay, now let's go through the paper to have an understanding of the workings of GraphRAG by Microsoft. From local to global, a GraphRAG approach to query focused summarization. So the abstract is interesting. Their point is that RAG fails on global questions directed at entire text corpus, which is what are the main themes in the dataset. So something that I call aggregation type queries. Generally, direct information type queries, general RAG is able to, or rather naive RAG is able to respond correctly, but RAG fails, or rather the naive RAG fails when the questions are kind of aggregation type queries where you need an understanding of the whole corpus. Prior QFS methods fail to scale to the quantities of text indexed by typical RAG systems. Their approach is to use an LLM to build a graph-based text index in two stages. First, to derive an entity knowledge graph from the source documents, then to pre-generate community summaries for all groups of closely related entities. So this graph approach has been touted as or for solving the aggregation type query problem. So human endeavors across a range of domains rely on our ability to read and reason about large collections of documents, often reaching conclusions that go beyond anything stated in the source text themselves. So basically, we as humans are able to infer things and logical conclusions from big bodies of information. So this is the pipeline stage of GraphRAG. There is source documents. This goes through a text extraction and chunking. Text chunks are generated. After this, domain tailored summarization is done to find element instances. Then domain tailored summarization is done to find element summaries. Then community detection takes place. We have the graph communities. Then again summarization is done to get community summaries, and again query focus summarization is done to get community answers. Again, those community answers are again summarized to find the global answer. So these steps till community summaries are done during indexing, and when query is taken, we get the community answers and the global answer. GraphRAG pipeline uses an LLM derived graph index of source document text. This index spans entities, edges, relationships, and covariates. Claims to have been detected and extracted and summarized by LLM prompts. So the Leiden algorithm is used to partition the graph index into groups of elements, nodes, edges, covariates that the LLM can summarize in parallel at both indexing and query time. This global answer to a given query is produced using a final round of query focused summarization over all community summaries to get the relevant response. So, as I was saying, the current track is an established approach to answering user questions over entire datasets, but it is designed for situations where the answers are contained locally within regions of text. So, this works because of the way the general RAG works. And this part is interesting. So, how graph communities are created from element summaries. The index is created in the previous the index created can be modeled as a homogeneous undirected weighted graph in which entity nodes are connected by relationship edges with edge weights representing the normalized counts of detected relationship instances. So to create this graph community, they use the Leiden algorithm. So the Leiden graph algorithm is an interesting algorithm. Each node, first step one, first each node in the network is assigned to its own community. Next, we decide which communities to move the nodes into and update the partition P. Then we assign each node in the graph to its own community in the new partition called P refined. Poorly connected communities are separated out. Then we have the refined partition to aggregate the graph. Each community in P refined becomes a node in the new graph, which is called G aggregate. Updating the partition P using the aggregated graph, we keep the communities from partition P, but the communities can be separated into multiple nodes from the refined partition P refined. We continue repeating the above steps until each community consists of only one node. In the final step for GraphRAG, summaries are generated. The next step is to create report-like summaries of each community in the Leiden hierarchy using a method designed to scale to very large datasets. So how an answer is created when a user query comes in. The community summaries that we have are used to generate the final answer in a multi-stage process. The hierarchical nature of the community structure also means that questions can be answered using the community summaries from different levels, raising the question of whether a particular level in the hierarchical community structure offers the best balance of summary, detail, and scope for general sense-making questions. So this is something that they claim. We'll have to test and see if this is actually correct. So for a given community level, the global answer to any user query is generated as follows. Prepare community summaries. Community summaries are randomly shuffled and divided into chunks of pre-specified token size. This ensures relevant information is distributed across chunks rather than concentrated and potentially lost in a single context window. Map the community answers, generate intermediate answers in parallel, one for each chunk. The LLM is also asked to generate a score between 0 and 100, indicating how helpful the generated answer is in answering the target question. Reduce to global answer. Intermediate community answers are sorted in descending order of helpfulness score and iteratively added into a new context window until the token limit is reached. So somewhat of a re-ranker is also used. So something that they are claiming is when comparing community summaries to source text using GraphRAG, community summaries generally provide a small but inconsistent improvement in answer comprehensiveness and diversity, except for root level summaries. So rather than evolution, these two are more interesting. I found these two more interesting. We consistently observed GraphRag achieve the best head-to-head results using other methods, but in many cases, the graph-free approach to global summarization of source text perform competitively. So this is also something that they are also admitting, that even a graph-free approach can have good responses. So even though in the paper they compared with naive rag, ideally to me the comparison should have been with the subquery approach, where each subquery is resolved separately and then the final solution is done by taking the aggregate of the responses from the individual queries. This basically is an advanced rag approach. So in an enterprise and production setting, you will probably implement this advanced subquery method of the advanced RAG approach, and then see if graph RAG approach is giving any benefits on top of it. So essentially, by going through this paper, you can understand that in graph RAG, you basically build understand the entities in your corpus, build communities out of it, and then using these communities you answer user queries. In the future work, they mentioned that the graph index, rich text annotation, and hierarchical community structure supporting the current GraphRAG approach offer many possibilities for refinement and adaptation. The this includes RAG approaches that operate in a more local manner via embedding based matching of user queries and graph annotations, as well as possibility of hybrid RAG schemes that combine embedding based matching against community reports before employing the map reduce summarization mechanisms. Anyways, let's go through the code and see how the tool that they have open sourced, how we can use the tool that they have open sourced to create our own GraphRAG pipeline. Git clone from the original Microsoft GraphRAG repository. We need to clone the repo instead of doing something like pip install GraphRAG because GraphRAG internally does not support embeddings from Ollama, and we will need to make some code changes to get Ollama embeddings. LLM part works because Ollama supports OpenAI specification for the LLM part. Now go to graphrag /LLM OpenAI OpenAI embeddings LLM.py. Now copy the code from GraphRAG local ollama. In the code you can see we import ollama and we have a for loop over the inputs to extract the embeddings. We have that in a list and return the list. Once the code changes are done, pip install ollama and then pip install the GraphRAG repo. This will install the required dependencies and the repo. Installation progress. Once the installation is done, create the rag test project using the command python -m graphrag.index --init --root rag test. So rag test is our project folder. You can see here that we have a 16 GB GPU installed. I have seen that GraphRAG does not work with less GPU memory, so you need at least this much to create the project. Now install the Ollama backend. You will get the command in the Ollama website. Once Ollama is installed, run ollama serve to start the Ollama process. We will use llama3.1 instruct model as our LLM, so pull it from Ollama. Test and see if the llama3.1 is working fine. Once you have the LLM pulled, pull nomic embed text, which will work as our embedding model. Embedding model pull is success. If you do ollama less, you should see llama 3.1 and nomic embed models. If you don't see them, then there was some error in the download process and run the commands again. Now we'll change some configuration in settings.yaml file in ragtest project. The grade project GraphRAG local ollama has the required parameters. Create the input directory. We will place our text files with the information that we need to index inside this directory. Open the settings.yaml file. In the settings file, we primarily have two sections, the LLM section and the embedding section. Under the LLM, update model with llama 3.1. Here I am updating with nomic embed, but this is a mistake. We'll need to change this later. Update request timeout to 300 or 500 seconds. Update API base with localhost 11434/v1 where the ollama service is running. Then update the LLM concurrent request to 5 from 25 so that we are not bombarding the Ollama service. This is optional and depends on the capability of the server that you are using. Next, moving on to the embedding section, updating the embedding model to nomic embed text. Here we are rectifying our mistake and setting LLM model as llama 3.1 model, which is the correct LLM model. Update API base with the same localhost 11434, which is the URL of the Ollama service. Make the concurrent request for the embedding request as 5 as well. Now moving on, we'll update the chunk section, updating the size as 200 and overlap as 20, because otherwise our model will not be able to handle that. Play around with this parameter to find the best size and overlap. Under snapshots, update GraphML as true. GraphMLs will be saved as well. This can be utilized if we want to analyze and check the graphs that are getting created. Inside the input folder, creating a text file where we can save the required data. The file should be kept inside the input folder because this is mentioned in the settings.yaml file. If you have a different folder, input folder, you can change this setting parameter. Now run the command python -m graphrag.index --root dot. This will start the indexing process. The data has been parsed and divided into 29 chunks. The indexing process will take some time to complete. You can see all the entity creation, summarization, and final document creation getting completed. If there is any error when running, go through the logs to get an idea about the error. Now let's run a query on the index graph using the command python -m graphrag.query --root dot method global tell me about llama 3.1. In the output we have success global search response llama 3.1 overview. The llama 3.1 405 billion model is an open source AI model developed by Meta AI. Then the key features are also mentioned. The implications for AI research and development are mentioned. How the model was developed is also written in the output. Below, as you can see, to formulate this answer, there were 6 references and 10 relationships. Similar to the global method, we have the local method as well, but the answer that was generated was not noteworthy. Now in the next section, we'll see how to use the index graph in code. Before that, as a small side note, are you worried about your project career? Are you not getting the right projects or promotions that you deserve? Then book a meeting at topway.io/Joydeep. I have worked with more than 60 high achieving professionals to achieve their dreams. Don't believe? See the testimonials. So book a meeting and realize your dreams. The Microsoft developers have shared the notebook to run global search as part of code. Import OS, import pandas as PD, import tick token. From GraphRAG, we import read indexer entities and read indexer tokens. To connect with the LLM, we have the chat OpenAI. Then there is the global community context to build global context based on community reports. Then there is the global search, which is a search engine to retrieve relevant community reports, extract key points, aggregate them, and generates a final response based on the aggregated information. This gives good understanding of questions that requires an understanding of the whole data. For creating the LLM instance, we need to provide the API key, which can be anything, API base, which is the ollama backend URL, and the LLM model, which is llama 3.1. We create the LLM model using chat OpenAI using the arguments that we just discussed. The API type is chat OpenAI API type. Since it's a Microsoft release, the other option is Azure OpenAI. Max retries is 20. setting the token encoder using tick token. Now load the community reports as context from the global search. Load entities using the create final nodes and create final entity tables from the indexing engine to be used for calculating community weights for context re-ranking. If not provided, use the rank attribute in the community reports table for a context ranking. Setting the input directory to the specific path where the reports are generated. Check the logs for this path. Part to the community report table, part to the entity table, and part to the entity embedding table. Community level in the Leiden community hierarchy from which we will load the community reports. Higher value means we use reports from fine-grained communities at the cost of higher computation cost. Load the entity DF, load the report DF, load the entity embedding DF, load reports and entity using these data frames. We see that the total report count is 2 and the report count after filtering is also 2. So our overall data is quite small, but creating this much took a long time, which is the main demerit of this pipeline. Go through the data and check if you like the communities that are generated. Set the context builder using global community context. For this we pass the reports and entities. Now we will perform the global search using the same parameters that we set when indexing the graph. Instantiate the search engine, which is an instance of global search. Run the query, tell me about llama 3.1. Takes around 30 seconds to generate the answer. It has the llama 3.1 overview talking about open source model developed by Meta AI with context length of 128K. Key features are custom agents, model distillation, and synthetic data generation. Implications are improved data accuracy and enhanced user experience. We have 6 references for this query and 10 relationships. Go through the context data of the result. Since there are only 2 reports, only 2 LLM calls have been made. In case there were more reports, more calls would have been there and the answer generation would have taken more time. So this is the overall code. In this video, we talked about GraphRAG paper, how to index your own data and how to use the indexed data, entities and relationships in code. The GraphRAG approach is a nice way to solve aggregate type questions which requires an understanding of the whole data. But the problem with this approach is that it is very slow. Try this method on your own data and let me know what you think in the comments below. I have used Ollama here with llama 3.1, but you can use other backends as well. I have another video where I installed other LLM backends such as OpenLLM and llama file. You just need to see if the backend supports OpenAI compatible LLM and embedding API. If not, maybe you might need to change some code as well, as we did in the video for the embedding part. Thanks for watching this video. Have a great day.